66 million years ago, on what was probably just an ordinary Tuesday, the sky cracked open. A rock the size of a city came screaming through the atmosphere at 40 times the speed of a bullet. The impact released more energy than 1 billion nuclear bombs. Within hours, the world was on fire. Within weeks, the sky went dark. And within a geological blink of an eye, the dominant species on Earth was gone. We call that the end of the dinosaurs. Most people think of it as ancient history, a one-time event, something that couldn't happen again. But here's what nobody tells you. It has happened again, many times. And the next one? It might already have our name on it. To understand just how violent Earth's past really is, you have to leave the history books behind and start reading the rocks. In Ontario, Canada, there's a region called Sudbury. From the ground, it looks like a city. But from space, it looks like a scar. 2 billion years ago, a meteorite roughly 10 kilometers wide punched into the Earth's crust with such force that it created a crater over 200 kilometers across. The impact was so violent, it melted the bedrock. What you see in Sudbury today isn't a city built on land. It's a city built inside a wound. And then there's Vredefort, South Africa, the largest confirmed impact crater on the planet, over 300 kilometers wide, more than 2 billion years old. The rock that caused it was so massive that geologists believe the explosion could have been felt on the opposite side of the globe. These weren't close calls. These were direct hits, catastrophic, world-altering, and they happened right here, on the planet we call home. So the question isn't whether Earth gets hit by massive space rocks. The question is, when is the next one coming? For most of human history, we had no warning system, no telescopes powerful enough, and no satellites scanning the dark. We were, essentially, sitting in a room with no smoke detectors. Then, on February 15th, 2013, at 9:20 in the morning, the city of Chelyabinsk, Russia, got a reminder. A meteor roughly 20 meters across, smaller than a house, entered the atmosphere at 60 kilometers per second and detonated in an airburst high above the city. The explosion released 30 times the energy of the atomic bomb dropped on Hiroshima. Windows shattered for miles. Buildings cracked. Over 1,600 people were injured, most of them by flying glass as they rushed to their windows to see what the flash was. Here's the thing that should keep you up at night. Nobody saw it coming. Not one single tracking system on Earth had detected it. And it came in from the direction of the sun, a blind spot that our entire planetary detection network simply cannot see. The Chelyabinsk meteor was small, a minor event in cosmic terms, but imagine what we might be missing. After the close calls, the international scientific community made a commitment. We would map the sky, every rock, every object, every potential threat. Today, NASA's Center for Near-Earth Object Studies, CNEOS, tracks hundreds of thousands of space rocks in real time. Scientists call them NEOs, near-Earth objects. Any asteroid whose orbit brings it within roughly 195 million kilometers of the Sun gets added to the watch list. The tracking systems are genuinely impressive. Radar telescopes, wide-field cameras scanning millions of square degrees of sky every night, algorithms that calculate orbital paths decades into the future. But here's the honest truth about those calculations. Orbital predictions for asteroids are only reliable for about 100 years. Beyond that, small gravitational nudges from Jupiter, from Saturn, even from the gentle pressure of sunlight, can shift a trajectory enough to turn a near miss into something else entirely. And that blind spot? The one that let Chelyabinsk sneak through? It's still there. Anything approaching from the inner solar system, from the direction of the sun, is essentially invisible to our ground-based telescopes. We are watching 80% of the sky with extraordinary precision and completely ignoring the rest. Not all asteroids are equal. That scientists categorize near-Earth objects by size and orbit. The ones that really matter, the civilization-level threats, are rocks larger than 1 kilometer across. An impact from something that size wouldn't just devastate a region. It would alter the global climate. It would collapse food systems. It would be, in the truest sense of the word, catastrophic. The good news? We've cataloged about 95% of those large objects, and right now, none of them are on a collision course with Earth. The not-so-good news? The smaller ones, rocks between 50 and 300 meters, are far harder to detect, and there are potentially tens of thousands of them we haven't found yet. Something in that size range wiping out a major city isn't science fiction. It's physics. Scientists estimate a rock large enough to devastate a metropolitan area hits Earth roughly every few hundred years. The last major airburst event before Chelyabinsk was the 1908 Tunguska event in Siberia. An explosion so powerful it flattened over 2,000 square kilometers of forest. The math is simple. The question is always the same. Are we overdue? For centuries, this was a problem with no solution. A rock was coming, and there was nothing you could do. That changed on September 26, 2022. So NASA's DART spacecraft, the Double Asteroid Redirection Test, traveled 7 million miles through space and deliberately crashed into a small asteroid called Dimorphos. Not to destroy it, not to blow it up, just to nudge it, to change its speed by a fraction and shift its orbital path. It worked. The impact changed Dimorphos's orbital period by 33 minutes, far exceeding the mission's target. It was the first time in human history that we intentionally and successfully altered the orbit of a celestial body. Think about that for a moment. For 4.5 billion years, Earth has been at the mercy of whatever the solar system decided to throw at it. In 2022, for the first time, we threw back. DART wasn't just a scientific achievement. It was a proof of concept. A statement. If we can find the rocks in time, and that's the critical condition, we can move them. Finding them in time. That's the whole game. And on that front, something extraordinary is about to happen. The Vera C. Rubin Observatory in Chile, currently in its final stages before first light, is set to begin the most ambitious sky survey in human history. Every few nights, it will photograph the entire visible sky. Its camera is so sensitive, so wide, that in a single image, it can capture an area of sky equal to 40 full moons. Scientists project that within the first year of operation, the Rubin Observatory will discover more near-Earth asteroids than have been found in all of recorded history combined. We're talking tens of thousands of new objects, cataloged, tracked, and added to the global watch list. That blind spot? A companion space telescope called NEO Surveyor, designed to operate closer to the Sun, is specifically built to look into the regions of sky that ground-based observatories simply cannot see. For the first time, we're building the infrastructure to actually know what's out there. Not guessing. Not hoping. Knowing. The asteroid that ended the dinosaurs wasn't a punishment. It wasn't a warning. It was just the universe, doing what the universe does. Indifferent, powerful, and ancient beyond comprehension. The difference between us and every species that came before is this: we can see it coming. And now, for the first time in Earth's 4 billion-year story, or we might actually be able to do something about it. The rocks are still out there, millions of them, drifting in the dark, on paths carved by gravity and time. Some of them will cross ours eventually. That's not fear-mongering. That's orbital mechanics. But for the first time in history, we're not just watching the sky and hoping. We're watching it and preparing.